So when cos 180 gives us minus 1, so this expression will be V is equal to minus 1 by 4 pi epsilon naught P divided by R square. Potential at P due to Q1 is given by V1 is equal to 1 by 4 pi epsilon naught Q1 divided by R1, because R1 is the distance between point P and Q1. Any surface where the potential is same everywhere, we'll call it as equipotential surface. Hello everyone, welcome to session 3 of chapter 2 Electrostatic Potential and Capacitance. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. In the last session, we have discussed about the potential due to an electric dipole, and we got the expression V is equal to 1 by 4 pi epsilon naught P divided by R square. Now let us discuss how does this varies with different values of angles, or when theta is equal to 0, what happens when theta is equal to 90 degree, what is the potential we get? Let us see now. The expression for potential due to an electric dipole is V is equal to 1 divided by 4 pi epsilon naught P cos theta divided by R square. Now, when theta is equal to 0, we have cos theta term here. So, cos 0 will be equal to 1. So, what happens to potential? It will be V is equal to 1 divided by 4 pi epsilon naught P divided by R square. Since this term cos theta will be equal to 1, the angle is 0. What if the theta value is pi, 180 degree? So, when cos 180 gives us minus 1, so this expression will be V is equal to minus 1 by 4 pi epsilon naught P divided by R square. Now, from these two expressions, we can write V is equal to minus or plus 1 divided by 4 pi epsilon naught P divided by R square for any point on equatorial plane. If we consider by drawing a point at from the midpoint or center of the dipole, we get theta is equal to pi by 2, and cos pi by 2 value is 0, because cos pi by 2 is nothing but cos 90, it is 0, then the entire value of potential will be equal to 0. So let's move on to the next topic, that is potential due to a system of charges, or we can say the superposition principle for the potential. For that we have considered a different charges Q1, Q2, Q3, Q4, Q5. These are the system of charges which are at a distance R1, R2, R3, R4 and R5 respectively from a point P. So now let us write the expression for potential at the point P due to various charges. Now the potential at P due to Q1 is given by V1 is equal to 1 by 4 pi epsilon naught Q1 divided by R1, because R1 is the distance between point P and Q1. Similarly, we get potential at P due to Q2, which is equal to V2 equals 1 by 4 pi epsilon naught Q2 divided by R2. Now we have, similarly we can write the expression for V3, V4, V5 by considering Q3, Q4 and Q5 respectively. But from superposition principle, the potential V at a point due to number of charges is equal to the algebraic sum of the potential due to individual charges. That is, V is equal to V1 plus V2 plus V3 plus and so on up to Vn. So now let us substitute in the place of V1 1 by 4 pi epsilon naught. V1 is due to the charge Q1 divided by R1 plus V2 term we have written in the slide. V2 is equal to 1 by 4 pi epsilon naught Q2 divided by R2. So I am substituting the same and so on. If you substitute for V3, you get 1 divided by 4 pi epsilon naught Q3 divided by R3. So like this, if you substitute up to Qn, you will get 1 by 4 pi epsilon naught Qn divided by Rn. Now from this, the term 1 by 4 pi epsilon naught is common in all. So I am taking that outside the bracket and writing the remaining terms inside. So we get V is equal to 1 by 4 pi epsilon naught Q1 by R1 plus Q2 by R2 plus and so on up to Qn divided by Rn. Now in this we can see that plus sign is common everywhere. So we can write in generally V is equal to 1 by 4 pi epsilon naught summation of, since we are doing sum of all these terms, so summation of I is equal to 1 to n. These are the limits Qi divided by Ri, where I is any integer. I can give the values like 1, 2, 3 and 4 up to n numbers. So this is the expression for the potential due to a system of charges. So the next important topic is equipotential surfaces. We must understand this concept, which is very important in the study of electrostatic potential and capacitance. So equipotential, the names only suggest the meaning of this term, which means any surface where the potential is same everywhere. We'll call it as equipotential surface. An equipotential surface is a surface with a constant value of potential at all the points on a surface. There are few properties of these equipotential surfaces which are very important examination point of view. So generally equipotential surfaces for a point charge is represented as concentric circles, and we can see here the potential electric field is directed outwards and the field is always normal and the potential is same at every point. So from this slide we can understand it better that the equipotential surfaces of a single point charge are the concentric spherical surfaces with charge at the center. You can see here the charge at the center. Equipotential surfaces are the concentric circles for a single point charge by keeping it in the center, and in this also the potential is same everywhere and the electric field is normal. What if we consider a dipole? So when you consider a dipole which are two charges, they are of different kind or the opposite kind, they tend to attract towards each other, and we can see the closer and closer lines towards this end and this end. When you consider dipole, you must keep in mind that the intensity is high when they are tending to come closer. Now equipotential surface for two identical charges, if you consider same charges, identical means plus and plus I have considered here, there must be a force of repulsion between these two and they'll go away from each other, and hence the intensity in this direction will be more and here it is less. So this is how you have to represent the equipotential surfaces for various type of charges diagrammatically. We have one more scenario that the equipotential surface for a uniform electric field are plane normal to x-axis. You can see here they are plane normal to x-axis. This is one more condition of representing an equipotential surface diagrammatically. So as I have mentioned, there are few properties of this equipotential surface which is very important to understand, and it says that electric field is always normal to the equipotential surface. If this is an equipotential surface, the electric field is always normal to it, and all points of equipotential surface are at same potential. The name says equipotential. So all points on the equipotential surface will have the same potential. Since the potential is same, if you take the difference between any 2 points, we will get zero value, which means the potential difference between any 2 points on an equipotential surface is 0. Since the potential difference is 0, that is VA minus VB, which is equal to potential difference delta V, which is equal to 0, then work done to bring a unit positive charge will be equal to 0, and hence we say that no work is done in moving a charge from one point to another point on the equipotential surface. So these are the very important points to remember, and this will be asked for 3 mark in examination. Electric field is always normal to the equipotential surface. All the points of equipotential surface are of same potential. No work is done in moving a charge from one point to another point, since the potential difference between any 2 point charges is 0. Next, we know that the component of electric field is always normal to the equipotential surface. So we can say the electric field component along the equipotential surface will be 0. So these are the properties. So let's move on to another important derivation, that is relation between electric potential and electric field. Relation between electric potential and field, which means if we get a relation, then it must contain electric field term and electric potential term, which means V term and E term. So let us now derive it. For this I have considered 2 equipotential surfaces with a potential V and V plus dV respectively. I have considered 2 equipotential surfaces and I named them as A and B. They have a potential V and V plus dV respectively. And I'll consider one more point P on the surface of B here, which is at a distance of dx from A. So P is a point placed on the surface B and which is located at dx normally from point A. Now E is the electric field due to a positive test charge. So now what is the work done in moving a charge Q from B to A? There is a charge Q at B. What is the work done in bringing the charge from B to A? So work done can be calculated by the formula dW is equal to F into dx, where F is the force and dx is the displacement. But I have represented this with a negative sign because I am bringing a charge from B to A and the direction is just opposite to the direction of electric field, and hence I have represented this with a negative sign. So from this we can write the potential difference. Potential of B is V plus dV and potential of A is V. So V plus dV minus V, this is nothing but the potential difference, is equal to work done divided by charge moved, that is dW divided by Q. Now simplifying this we will get, so we have V plus dV minus V is equal to dW divided by Q. So cancelling plus V and minus V, we get dV is equal to dW divided by Q, and that's my equation 2. Now substitute equation 1 in 2 and we will get, what is our equation 1? It is dW is equal to minus F into dx. So substituting the same here, we will get dV is equal to, in the place of dW I am substituting minus F dx. So we get dV is equal to minus F dx divided by Q. Or from this we can write, we know what is F here, it is force. What is that force? It is nothing but electric field or electrostatic force. So it is due to electric field. So here we have a term F, but we know electric field E is equal to force experienced by unit positive charge, and from this we can write F is equal to E into Q. So this expression becomes dV is equal to minus E into Q into dx divided by Q. So Q and Q will get cancelled and we remain with EV is equal to minus E into dx. But we need a relation between electric potential and electric field. So let us just replace these terms and we get E is equal to minus dV divided by dx, where the negative sign indicates that the direction of electric intensity E is in the direction of decreasing potential. So this is the relation between electric field and potential. So another important term to understand is a potential gradient. What is the meaning of potential gradient? It is nothing but the change in potential per unit displacement normal to the equipotential surface. The change in potential, dV is nothing but change in potential per unit displacement. Dx is a unit displacement normal to the equipotential surface is called as potential gradient. So it is represented in vector form, that is E is equal to modulus of dV by dx, where E is electric field, dV is change in potential and dx is a displacement. And for this the SI unit is volt per meter, because we have a potential, that is SI unit of potential is V, and distance or unit displacement, the SI unit is meter. So from this we will get volt per meter. So this relation E is equal to minus dV by dx is valid for non-uniform field also. So there is no condition that E is equal to minus dV by dx is applicable for only uniform fields, but it is also applicable for non-uniform fields also. So electric potential, as we all know, is a scalar quantity, but the thing, potential gradient is always a vector, and the SI unit for potential gradient is volt per meter. So in this session we have learnt few important topics with respect to equipotential surfaces, and in the upcoming sessions let us learn some more interesting concepts. Until then, keep learning all of you. See you all in the next session. Thank you.